Bismillah ar-Rahman ar-Rahim. This is a probability problem. We have a vector x with two or more elements. The elements are real valued. Given vector x, we can construct vector y. The components of vector y are y1 to yk. K is a positive integer between 2 and n. The components of vector y are taken from vector x. Specifically, y is xi1, xi2, all the way to xik. The indices from i1 to ik are positive integers between 1 and n. The sequence i1, i2, and so on is strictly increasing. This means that in vector y, the original order in vector x is preserved. We are interested in y vectors that are alternating. If y is two-dimensional, that is, it contains two elements from vector x, then by definition, it is alternating. If y has three elements or more, the consecutive differences must be alternating in sign. Consider elements in vector y, ym plus 1, ym plus 2. M is a positive integer between 1 and k minus 2. For vector y to be alternating, it must be the case that for every possible value of m, ym plus 2 minus ym plus 1 times ym plus 1 minus ym, the product of these two differences must be strictly negative. If this bracket is positive, the other is negative and vice versa. If this is true for every m, then vector y is alternating. For instance, consider three-dimensional vector x with components 1/4, 1/3, and 1/2. The possible y vectors that are two-dimensional are these three vectors: 1/4, 1/3, 1/4, 1/2, and 1/3, 1/2. Can we construct using vector x an alternating vector y with three components? 1/3 minus 1/4 is positive, 1/2 minus 1/3 is positive. The differences do not alternate in sign. We cannot have a three-dimensional alternating vector y. Define z of n and x. This is a function that needs a vector x with a number of components n. Z of n and x is the maximum number of elements alternating vector y can have when it is constructed using the n-dimensional vector x. In this example here, z of 3 and this vector x is equal to 2 because there is no alternating three-dimensional vector y that can be obtained using this particular vector x. Suppose now that x is this vector with components 1/4, 1/2, and 1/3. We have three alternating two-dimensional vectors, 1/4 and 1/3, 1/4 and 1/2, and 1/2 and 1/3. Can we have a three-dimensional vector y that is alternating? 1/2 minus 1/4 is positive, 1/3 minus 1/2 is negative. This condition is satisfied, and if we take vector y as vector x itself, we do have an alternating vector. The possible alternating y vectors are these four vectors. Three of them are two-dimensional, the fourth is three-dimensional, z of 3, and this particular x vector is equal to 3. Let x be an n-dimensional random vector whose components are independent and identically distributed uniform random variables, uniform over the interval from 0 to 1. Vector x now is generated randomly. The components are IID. Each component has a PDF that is equal to 1 from 0 to 1, 0 elsewhere. Now let's focus on four-dimensional vectors. For every vector x, z of 4 and x is the maximum number of components alternating vector y can have, and y is constructed using vector x. Because x is a random vector, this quantity now is random. We are interested in the PMF, the probability mass function of z and 4 and x. What are the possible values of z and 4 and x? Without knowing anything about vector x, we are sure that z of 4 and x can be equal to 2, because by definition, the two-dimensional subvectors extracted from x are alternating. It may happen, depending on the elements of vector x, that we have an alternating vector that is three-dimensional. The last possibility is that vector x itself is alternating with consecutive differences that alternate in sign. In this case, z of 4 and x is equal to 4. The question now is, what is the probability that z of 4 and x is equal to 2? What is the probability that this discrete random variable is equal to 3? And what's the probability that it is equal to 4? In the second part of the question, we do not fix the number of dimensions at 4. We solve for a general n. We need to obtain the first moment or the expectation of z of n and x. When you think about the problem, you will discover that what is really important is that the elements of vector x are absolutely continuous random variables. The fact that they are specifically uniform is not important, as we will see. If the elements of random variable x are Gaussian or exponential, we will get the exact same result. The advantage of having the components of vector x as absolutely continuous random variables is that the probability that any two of them are equal is 0. So from the very beginning, we can think about vector x with distinct components that are all different from one another. The elements of vector x are distinct with probability 1. There are 4 elements in vector x and 4 factorial, that's 24 permutations. What is the probability that z of 4 and x is equal to 2? What should happen so that the only alternating y vectors we can construct using vector x are two-dimensional? Y is two-dimensional only if the elements of vector x are strictly increasing or strictly decreasing. So suppose that vector x has increasing elements. You are constructing vector y, you take x1 and x2. The difference x2 minus x1 is strictly positive. What is the problem? If you choose x3 or x4, x3 or x4 minus x2 is also positive. You do not get an alternating vector. The same will happen if the components of vector x are strictly decreasing. There are two arrangements of the elements of vector x, 2 out of 24, that makes z of 4 and x exactly equal to 2. This probability is 2 over 24, which is 1 over 12. Because we know that z of 4 and x has 3 possible values, the sum of the 3 probabilities is 1. We can skip the possibility that z is equal to 3 and focus on the case z equal to 4. If we obtain the probability of z being equal to 4, the probability that z of 4 and x is equal to 3 is 1 minus 1 over 12 minus the probability that z of 4 and x is equal to 4. The first two elements in vector x satisfy that x1 is strictly greater than x2, or that x1 is strictly less than x2. The probability that x1 is equal to x2 is 0. If we want z of 4 and x to be equal to 4, and x1 is greater than x2, then we want x3 to be greater than x2, and we want x4 to be less than x3. If x2 is greater than x1, z is 4. If x3 is less than x2, and if x4 is greater than x3. Among the 24 orderings of vector x, how many of them satisfy this situation here? Here is vector x. Here is vector, say, x tilde, which is x in which the elements are placed in strictly descending order. x3 must be greater than x2 and x4. This means that if we take the elements of vector x and arrange them in descending order, x3 must be in the first two positions, because x3 needs to exceed both x2 and x4. On the other hand, x2 is less than x1 and is less than x3. x2 must be in one of the last two positions, because it needs to be less than x1 and x3. Here are the four possibilities for ordered vector x tilde. x3 is in one of the first two positions, x2 is in one of the last two positions. What about x1 and x4? To get z equal to 4, and if x1 is greater than x2, we need x4 to be less than x3. The only possibility here is to have x4 as the smallest element in vector x, the minimum, and x1 as the maximum. Nothing else. If we come to this configuration, again, x3 must be superior to x4. We must have x4 here and x1 there. x1 should be greater than x2. I cannot put x1 here, so here it is, and x4 is the minimum. If x2 is the minimum and x3 is the maximum, if we put x1 here and x4 there, we obey these inequalities. We also obey them if we swap x1 and x4. If x3 is maximum and x2 is minimum, we don't care about the particular relation between x1 and x4. The inequalities here that make z equal to 4 correspond to 5 orderings of vector x. Let's have an example based on this ordering. So this is vector x itself. x1 is maximum. Let's say that x1 is 0.9. x3 is second largest and is equal to 0.8. x2 is 0.7. And x4 is the minimum, say it is 0.5. 0.7 minus 0.9 is negative. 0.8 minus 0.7 is positive. 0.5 minus 0.8 is negative. Vector x itself is alternating. Z of 4 and x is 4. If we study these inequalities, we get 5 more orderings. Among the 24 ways in which the elements of vector x can be ordered, there are 10 ways such that z of 4 and x is equal to 4. The probability of this event is 10 over 24, which is 5 over 12. Automatically, the probability that z of 4 and x is equal to 3 is 1 minus 1/2, which is 1/2. When I did this example, I used numbers between 0 and 1 because the problem says that the components of vector x are uniform over the interval from 0 to 1. But we don't really care about the exact distribution so long as the IIT components of vector x are absolutely continuous random values. Now we focus on a general number of components in vector x. The way I solve the problem is using recursion. I try to relate z of n and this n-dimensional vectors with components from x1 to xn to z of n plus 1, and then we have the exact same vector with one extra component, xn plus 1. Here is x transpose. N is equal to 8. We want to extract from vector x alternating vector y with the maximum possible number of components. To do this, we track the increasing and decreasing patterns inside vector x. The subsequence 6 and 3 is decreasing. The subsequence 3, 7, and 8 is increasing. 8, 5, 1 decreasing. 1 to 4 increasing. This allows us to obtain an alternating vector y with 5 components. For instance, we can take 6, 3, 8, 1, and 4, and this will be our vector y. The difference is negative, then positive, then negative, then positive. If we replace 8 by 5, vector y is still alternating. If we replace 1 by 2, vector y is still alternating. All these vectors are 5-dimensional. Our interest is in the number of components. Imagine that we increase the number of elements in vector x by 1. We keep the first n components. We have an extra element eta to be placed in position n plus 1 in the new vector x. We have that z of 8 and this vector x equal to 5. What about z of 9 and this 9-dimensional vector with those components and eta? Is this z equal to 5 or can we increase it? The answer depends on the value of eta. If eta is greater than 4, z is 5. For example, if eta is 13 and this is the new vector x, we can change this 4 to 13, but vector y is still 5-dimensional. We cannot have 4 and 13 because 4 is greater than 1 and 13 is greater than 4, thereby violating the definition of being an alternating vector. This 4 can be changed to 2. It can remain as is. It can be changed to 13. We can have any one of these 3 guys as the last component of vector y. In all cases, z is equal to 5. This is when the last component in vector x, xn plus 1, is greater than this 4. What if we get a 0 here or something less than 4? In this case, we can have a 6-dimensional alternating vector y. Z is increased by 1. Here is another vector x. That's the increasing and decreasing pattern inside the vector. The vector is alternating, so we can choose vector y to be equal to vector x, z of 8, and this vector is equal to 8. If we increase the number of components by 1, if we get something less than 0, that's it. If we get, say, minus 1, vector y may have 0 as the last component or minus 1, but it cannot have both. On the other hand, if the new component is greater than 0, say 11, then we can increase the length of vector y by 1. What can we conclude from this investigation? Let this expectation with n-dimensional vector x be beta n. If we append one component to vector x, now we have n plus 1 components. Let's call the expectation beta of n plus 1. I would say that beta n plus 1 is equal to beta n, or it is equal to beta n plus 1. It is equal to beta n plus 1 if the extra element can be added to the alternating vector y. Beta n plus 1 is equal to beta n plus 1 times the probability that I can take this extra element in vector x and put it in vector y, so that z is incremented by 1. The question now is, what is this event exactly? In this example, the last element is strictly less than the element before it. We don't have an increase in the value of z if we get an element that is less than 0, less than the last element. In that example, the last element is greater than the one before it. We are unable to increment z by 1 if we get something greater than 4. Thus, beta n plus 1 is equal to beta n plus 1 times the probability that the random variables xn minus 1, xn, and xn plus 1 do not form a monotonically increasing or decreasing sequence. If the 3 taken together give us an increasing or decreasing sequence, z remains as is. Otherwise, we can increase z by 1. If you have 3 IID random variables, they can be arranged in 6 ways, 3 factorial. In 2 orderings out of the 6, we get a sequence of 3 elements that is either strictly increasing or strictly decreasing. The probability of this event here is 4 over 6, 2/3. Beta n plus 1 is equal to beta n plus 2 over 3. If vector x is 2-dimensional, then z of 2 and x is 2 with probability 1. The expectation is 2, beta 2 is equal to 2. Based on this recursion or difference equation, beta 3 is beta 2 plus 2/3. Beta 4 is beta 3 plus 2/3. Beta n is beta n minus 1 plus 2/3. Add the sum of betas from beta 3 to beta n is equal to the sum of betas from beta 2 to beta n minus 1. We have 2 over 3 added to itself, n minus 2 times. Cancel the terms that are on both sides. We are left with beta n equal to beta 2, which is 2, plus n minus 2 times 2 over 3, which is 2 over 3, n minus 2 plus 3. That's 2 over 3 times n plus 1.